Good afternoon. We're going to do the notes for 5758, which is imaginary and complex numbers. Some of this is a review of what we've already learned. Other pieces are going to be new. You will need graph paper for the final part of the notes and a ruler, so you might want to get those out and pause the video. Okay, so Roman numeral 1, we're going to start with the imaginary unit. And the imaginary unit was originally designed as a solution to a long-standing and classic dilemma. So the dilemma is when you're being asked to solve with a square root, or because you're going to take a square root of both sides, but it's equal to a negative number. And what happens is when you take a square root of both sides, you've got x equals the square root of a negative 1. That isn't actually going to be possible because a positive 1 squared is a positive 1, and a negative 1 squared is also a positive 1. So there's no way that we can get a negative 1 out of a square. So x can't be 1, x can't be negative 1, there is no solution possible. So along comes the imaginary unit, which is designated with an italicized lowercase I, and I is the square root of negative 1, which means that I squared is automatically a negative 1. In addition to the imaginary unit coming along, they also established the standard form of a number that has an imaginary unit, which is a plus and minus bi, where a is the real part, I is the imaginary part. When you are simplifying numbers with an imaginary unit, you can make the replacement radical negative 1 with an I, but what has to be removed is anytime you get an I squared. Anytime you get an I squared, you have to replace the I squared with a negative 1, which will automatically make that part of your answer real. Remember, the symbol for real is a capital R with a bar through it. Okay, so let's do an example. So example 1. We're going to simplify 2 square root negative 1 plus square root negative 1. So remember that the scalar is being multiplied by the radical. We make the replacement of I for the radical negative 1, and this gives us 2I plus I. And then you add them just like it was 2x plus x. 2I plus I is 3I. And that would be your answer. If you're asked to put this into standard form, it would be 0 plus and minus 3i, because there isn't a real part, so we represent with a 0. You can also represent a regular number, like 7, as standard form. The 7 would be the real part, plus and minus 0i. You would make the imaginary part a placeholder 0. Okay, so let's go into some additional examples. So example 3. Let's say you've got the square root of negative 7. So to simplify this, you're going to split or factor the negative 7 into 7 times negative 1, which is basically prime factoring. Then you split the radical, so radical 7 times radical negative 1. By separating out the radical negative 1, it gives you something to replace with I, because I equals the square root of negative 1. So we replace, and that gives us radical 7 times I, which in standard form would be 0 plus radical 7 I. If you are not in standard form, then it would just be radical 7I, or occasionally you'll see I radical 7, but not commonly because it isn't standard form. Okay, let's do another example. Let's say you've got the square root of negative x minus 2. So first thing you want to do is factor out the negative 1. So this becomes x plus 2, and then the factored out negative 1 goes second. Then you're going to make the replacement with I. So that gives me radical x plus 2 times an I. And so that is my answer, the square root of x plus 2 with an I outside of the radical bar. All right, let's do another example. Example 5. Okay, example 5, you have a negative square root of a negative 4. So your first step is the same, you factor. So 4 is 2 times 2, and then we get a negative 1 factor. Now we split, so the radical 2 times 2 gets split from radical negative 1. On the real part, 2 2's, 1 comes out to the front. It gets multiplied by the negative, so it's a negative 2. And then we replace the square root of negative 1 with I. So our answer is negative 2I. Okay, example 6. Let's say you've got square root of negative 2 times 5I. All right, so you're going to treat the radical the same exact way. We're going to factor out the negative 1. So I have 2 times the negative 1. Then we're going to split the radical into radical 2 times radical negative 1. The radical negative 1 gets replaced by an I. So now we have radical 2 times I times 5I. All the exterior numbers get multiplied together and move to the front. So I have a 5I. So 5I squared, radical 2. And then remember that I squared equals negative 1. That has to be replaced. So we're going to replace I squared with a negative 1. So that gives me a negative 5 radical 2. There is your answer. All right, Roman numeral 2. We're going to do some complex number math. And complex number math is really the same exact math that you would do with x's. The only difference is if you get an I squared, you have to replace. Otherwise, these are just like simplifying anything else. There isn't anything fancy. So example 1, we're going to simplify 3 plus 4I plus negative 7 minus 2I. Okay, so when you distribute a positive, nothing changes. So we have 3 plus 4I minus 7 minus 2I. And then you're going to add together the real parts and add together the imaginary parts. So here we go. 3 minus 7 is negative 4, and 4I minus 2I. 4I minus 2I is 2I. And that would be your answer. All right, let's do another one. Example 2. We're going to multiply 3 plus 2I times negative 5 plus 6I. So again, this is just like what we've practiced. We're going to distribute the 3. So 3 times negative 5 is negative 15. 3 times 6I is 18I. Now we're going to distribute the 2I. 2i times negative 5 is negative 10i. 2i times 6i is 12i squared. Draw a line and add like terms. So we have negative 15 plus 8i plus 12i squared. So far this is just like we would do it with x's and numbers, but now we're going to make the replacement. I squared is a negative 1, so we multiply 12 by a negative 1, and that gives us negative 12. So now the negative 12 is real, so we're going to put the reals together. Negative 15 minus 12 is negative 27, and then plus 8i. So multiply like normal and then make the replacement. All right, example 3. I think I'll put it right here. Example 3. All right, we're going to do division. So 2i minus 3 divided by I plus 2. So the first thing you're going to do is stack it up. So 2i minus 3 over I plus 2. And now this is where you're going to use what we call the complex conjugate. So conjugates are pairs of numbers. If you have a plus bi, the conjugate is automatically a minus bi. So it's the same but has a different sign in the middle. So the conjugate for I plus 2 is I minus 2. We're going to multiply the top and the bottom by I minus 2. Okay, so on the top, this is just multiplication again. So 2i times I is 2i squared. 2i times negative 2 is negative 4i. Negative 3 times I is negative 3i. Negative 3 times negative 2 is positive 6. On the bottom, I times I is I squared. I times negative 2 is negative 2i. 2 times I is positive 2i. 2 times negative 2 is negative 4. All right, now remember that we've got to replace the I squareds with a negative 1. So this makes the 2 a negative 2. 6 minus 2 is 4. And then negative 4 minus 3 is negative 7i. On the bottom, when you multiply by the complex conjugate, you can see that the single i's add to 0 and they are gone. So 2i minus 2i is gone. And now I have negative 1 minus 4, which is negative 5. So the complex conjugate makes the I disappear from the bottom of the fraction. When you divide, you cannot have an I in the bottom of the fraction. So now we're going to split this into standard form. It would be negative 4/5 plus 7/5 I. And that would be your answer. So that is division. So it's not traditional division, but it does get the I, the imaginary unit, out of the bottom of the fraction. Okay, last section. This is the one with the graph paper. Graphing complex numbers. Okay, so when you graph a complex number, you're going to use a Cartesian graph, also known as a rectangular graph. And when you're graphing complex numbers, remember that your standard form of a complex number is a plus bi. So when you graph numbers, the real part, which is the a, goes first. The imaginary part, which is the b, goes second. And on your graph, you can see that the x-axis is your real axis. That's where the x-coordinate goes. And the y-axis is your imaginary axis. All right, so we're going to do an example. We're going to graph the number 6 plus 4i. Okay, so 6 is the real part. 4i is the imaginary part. So we're going to go 6 to the right, 1, 2, 3, 4, 5, 6, and we're going to go up 4, 1, 2, 3, 4, and that is your point. Now when you label the coordinate, use parentheses and just write 6 plus 4i. Don't put a comma in or change it in any other way. All right, so one of the other things that they're going to have you do on your homework is they're going to ask you to find the absolute value of a complex number. They also might phrase it differently and say, find the distance of the point to the origin, which is actually the same math. And both of these processes, the absolute value and the distance of the origin, is the absolute value of a plus bi. And the formula for that is the square root of a squared plus b squared. And this has to do with triangle math. So if I take my ruler here and I draw from the origin to the point, and then I have, well, you actually can go either way, but you go to the right 6, you go up 4. This actually makes a right angle. So the distance from the origin to the point is the hypotenuse of the triangle. So if we label the legs, this would be A, this would be B, this would be C. And using Pythagorean theorem, A squared plus B squared equals C squared. So to find C, which is the distance to the origin, you take Pythagorean theorem, square root both sides, 2 c's, 1 comes out, and I'm left with the square root of a squared plus b squared. And that is where this formula comes from. It's just Pythagorean theorem. All right, so let's do our example. We're going to find the absolute value of 6 plus 4i, which is also the distance from the point to the origin. So here we go, using the formula, a squared is 6, so 6 squared, plus b squared, b is 4, don't put the I on it, just the 4. And then we simplify, 6 times 6 is 36, 4 times 4 is 16. Add them together, we get 52. Refactor the 52 to simplify the radical, and we get 2 times 2 times 13. So 2 2's, 1 comes out, the 13 is left in. So the distance from the point to the origin is 2 radical 13. You will notice that distance in this case is a real number. We're talking an actual distance. All right, that is the end of the notes. Have a good rest of your day.